Hey guys, this is our first day of honors physics, and I hope it's going well for you so far. This is the way that the notes are going to be provided. So each day I'm going to have a video up for you, and the video is going to go through a PowerPoint and some videos and some GIFs and stuff, as well as some practice questions. And you can find those videos on YouTube. You could always follow me if you want to. You could look on Canvas, and I'll also have them posted on CTLS. After we watch through these videos, then we'll do a live question and answer session, and of course, we'll do a little bit of warm up before these as well. So, with that being said, let's go ahead and get started. Today we're going to be talking about speed and velocity, but before we get to that, I want to start with a story from last year. Back in fall of last year, the physics department took a field trip to iFly. Of course, this was pre-COVID, pre-quarantine, all that. So we had to fill out this form for the buses to go to iFly, and the form asks, how far away from Sprayberry is the field trip? So took this big red line, drew it from Sprayberry to iFly, and the length of that is 9.5 miles. iFly is just about 9.5 miles as the crow flies from Sprayberry to iFly. But that's not what the bus was really after. The bus was looking for how far it had to travel. And the bus isn't going to go driving, barreling through houses and neighborhoods, as awesome as a movie that would make. It would be dangerous and wrong. So instead, the bus follows these roads, and it follows Sandy Plains Road to the west, and then, I-75 to the southeast, and it gets down to Smyrna, where iFly is. That path is 12.8 miles long, as you can see in the map here. So which one belonged on the form? 12.8 miles or 9.5? iFly is 9.5 miles away from Sprayberry, but the bus had to travel 12.8 miles. The problem was it was vague. And there are two different answers here. The distance that the bus needed to travel was 12.8 miles each way. Distance doesn't involve direction. It doesn't matter the overall where you end up versus where you begin. It's the path taken. So the path taken of the bus was 12.8 miles. However, how far away was the bus from where it began the day? And that is 9.5 miles. That is displacement. Displacement is how far away you are and in what direction from where you began. The reason we have to include direction is because displacement is a vector measurement. We'll come back to that idea in a little bit. So let's look at this route taken by this bicyclist. On Monday, the bicyclist goes directly from point A to point B. On Tuesday, he takes a meandering route, going to see the flowers and his friends, and makes it to point B, but only after a much longer path. On Monday, he goes a shorter distance than on Tuesday. Tuesday's distance is longer. However, on both days, he ends up in the same point and started at the same point. So the displacement on both days is the same. Take a look at this hedgehog. Run along. Now we get to the question, is he going fast? How can you tell if he's going fast? A couple ideas. Is it because his legs are all blurry right there? Because that could just be a frame rate problem with the camera, or more likely with the compression that was done to the film. What about, is it because his legs are going back and forth really quickly? That's another question of fast. I mean, couldn't we have a giraffe walking along beside him, moving just as fast, moving his legs much less quickly? So, what fundamentally determines whether he's going fast? His body, not his legs. And that is how far he moves in a period of time. Speed is measured as a distance over time. You may recognize from a car, a speedometer measures in miles per hour here in the States, or kilometers per hour in most of the rest of the world. Those are each distances over time. You could measure the speed of a bullet in miles per second, or maybe feet per second, right? Those would be distances over time. You could measure the growth of a mountain in millimeters per decade, distance over time. right? Any measurement of distance divided by any measurement of time gives you a speed, although you need to pick the right units for the rate at which something is changing. Thus, if something goes faster, we would expect for it to take less time to move the same distance. So if you're running the 100-meter dash, the shorter the time you run that 100 meters in, the faster you're going. In the same way, you can measure the opposite way. In the same period of time, someone going faster will have moved farther. You could imagine, two people saying we're both gonna run for 10 seconds, and at the end of 10 seconds, whoever's ahead must have gone faster, right? Now, it's important to note that the bus on its way to iFly moved at a speed. That speed doesn't determine direction. Those are two different things. Speed is a scalar measurement, which means direction is not part of it. The bus went west at one point. It went southeast at one point. It went southwest at one point. All these different directions. And we just don't worry about that because speed is a scalar measurement. Let's look at some other things that are scalar measurements. Maybe you're 16 years old. You're not 16 years old south, Maybe you have 2 cups of milk in the refrigerator. Well, you don't have 2 cups left in your left. You don't have two cups upward in your refrigerator. You don't need a direction with these measurements. So there are scalar measurements, and speed is a scalar measurement. Another idea we need to cover is the idea of average speed. If you run the 100-meter dash and we take the distance you go, 100 meters, divided by the time it takes you to run that 100 meters, that is an average speed. We're averaging out all this different speeds you're actually running at in there. You're probably running your slowest right when you come out of the blocks, right? You're having to speed your body up, accelerate it. You're probably running your fastest after a couple seconds. But we're not going to worry about all the little individual times. Instead, we're going to look at the average overall. And this becomes important later because we could also look at instantaneous speed, like how fast were you moving 0.7 seconds into the run. And for that, we would need a much smaller interval of distance and a much smaller interval of time. If you're taking calculus, you may recognize this is where we would be getting a limit. Instantaneous speed is very difficult to get, and so realistically, most of the measurements we get are averages, maybe bigger or smaller averages, but they're still averages. So, if I'm driving at 60 miles an hour, where will I be in 2 hours? I just start from Sprayberry, get in my truck, and I drive for 2 hours. Where will I be at the end? The answer is you don't know, right? Because 60 miles an hour is a speed, right? It's a speed. And does speed involve direction? No, because it's what kind of quantity? It's a scalar quantity. So, speed doesn't involve direction. It only has a rate of movement. If we include direction, like if I want to say I end up in Chattanooga, then we need to say I drive at 60 miles per hour northwest. 60 miles an hour northwest puts me around Chattanooga in a couple hours. So notice that by adding in the direction, I can now point to where I'll end up. This is what we call velocity. Velocity is speed with direction. So if we go back to our bicycle example, if we go from point A to point B on both days, and we do it in the same period of time, our velocity would be the same. Because in both cases, no matter what path we take, the displacement is the same, right? Displacement is that straight line path from where we begin to where we end. And it's the same on both Monday and Tuesday. Therefore, if we travel in the same period of time, we'd have the same velocity. Let's see an example of that. So which one was faster, the man or the train? And it depends, doesn't it? What do you mean by fast? If you were at that second train station, you saw them both arrive, and you could see the top and the bottom of the train station at the same time. They arrived at the train station at a pretty similar time, right? The train got there a little bit earlier, but they arrived there pretty quickly, one after the other. So who took the longer path then? Well, the runner took the longer path, right? He had to go up, out to surface level, run across surface level, go around buildings, and come back down. The train just went from where it started directly to where it ended. So if we're talking about speed, he covered a farther distance in just barely more time. So he had more distance in basically the same time, which meant he was faster. But what if we're talking about velocity? With velocity, do we care about the path? No. We care about where you began to where you ended. And the train and he ended and began in the same locations, right? They were both here, and then they both ended up at that second station down on the tracks, basically. So, which one got there first? The train did, right? So the train arrived first with the same displacement. Same displacement, train had less time, therefore the train had a greater velocity. The man had a greater speed, the train had a greater velocity. Do we see why? All right, let's do a couple practice problems. So first we have a man taking a walk. He's going to walk down the block 2 meters. It's not a very long block. Then he's going to turn, walk 2 meters east, a meter north, a meter east, and then another meter north. We want to calculate both his distance and displacement. So to get distance, we need to add up all of the paths he's taken. So he moves 2 meters south, then 2 meters east for a total of 4 meters, 5 meters, 6 meters, 7 meters. He has moved 7 meters. That's the distance. But is that his displacement? No. In fact, he moves 2 meters south and then later 2 meters north. So doesn't that cancel out? Leaving us with just 2 plus 1, a total of 3 meters going east. And in fact, if we were to draw a line from the beginning to the end, let's make a little dotted line here. Isn't this 3 meters long? And doesn't it go east? Next, we have a man following a curving path at a constant speed. Is his velocity changing? He's going at a constant speed, isn't he? But is velocity more than speed? Yes, it is both speed and direction. So the answer is yes, because the direction is changing. Now let's do a little bit of math. A runner finishes a 5K in 30 minutes. We want to calculate her speed. Let's start by writing our formula. Always write the formula first. Distance over time. Speed is distance over time. Let's plug in our numbers. The distance is 5 kilometers because that's the length of a 5K. That's why it's called a 5K. And the time is 30 minutes. So we can simply simplify by dividing by 5, and we get 1 over 6 kilometers per minute. But maybe that's a unit that you don't use all that often, kilometer per minute. So maybe let's turn it into meters per second. How can we do that? If we have 1 kilometer over 6 minutes, and we want to turn it into meters per second, we need to do a little dimensional analysis, right? Remember that from chemistry? So if we want to turn kilometers into meters, we need to put kilometers on the bottom, so this will cancel out, and meters on the top. And how many meters are in a kilometer? 1,000. And then we want to get rid of the minutes. The minutes are on bottom, so we'll put a minute on top. And then underneath, how many seconds are in a minute? That would be 60. So let's do our crossing out. 1 kilometer and 1 kilometer will cancel out. Minutes will cancel out with minutes. And we're left with 1,000 meters divided by 6 times 6 is 36, 360 seconds. 1,000 meters divided by 360 seconds, so 1,000 divided by 360. Type that in real quick, and we get about 2.8 meters per second. Not a bad rate. Now, let's go to another runner circling a 400-meter track, the type that is out there around the football field, going around that 400-meter track in 30 seconds. We want to calculate both his speed and velocity. So the first thing we do again is write the formula. Speed equals distance over time. Speed equals the distance, which is 400 meters, divided by the time, which is 30 seconds. 400 divided by 30. So 40 divided by 3, that's 4/3 times 10, which is like 13-ish, something like that. 13-ish, 13.3. Now I've got the calculator done. Meters per second. That's how fast he was going. But what's his velocity? Velocity is displacement. We can use the delta x to represent displacement over the change in time, delta t. What's his displacement from the beginning to the end? How far away is he from where he started? Isn't he exactly where he started? So his displacement is 0. Again, the reason for that is because he ended up where he began. He went in a circle. He ended up at the same point on the track where he started. So his displacement is 0. And 0 divided by anything is, oops, that's a t, is 0. So his velocity is 0. Make sure you ask questions if you have them in the